Every single time you tap the screen of your smartphone or like you open a program on your laptop or even just ask your smart speaker for the weather, there is this microscopic, highly synchronized symphony happening inside your device's computer chip.
Oh, yeah. Yeah.
And I mean, literally microscopic. We take it completely for granted. You tap, it works. But today, our mission is to uncover exactly how that incredible synchronization is engineered. So, welcome to the deep dive.
Thanks. It really is a hidden world, honestly. The sheer scale of the coordination required just to make like a simple app open without crashing.
Yeah.
It's staggering when you look at the physical architecture.
Right.
We are talking about billions of tiny electrical signals flying around an area the size of a fingernail.
Yeah, it's wild. And to guide us through this hidden world, we are looking at a stack of highly technical slides and visual blueprints we've gathered.
Okay.
They're titled Blueprint to Silicon, the DME algorithm, and they also outline a Python implementation specifically called FSD's Pi for something called clock tree synthesis.
Yeah, and we are going to be translating a very dense mathematical and algorithmic framework into what is honestly a mind-blowing look at the hidden geometry of microchips.
Definitely.
I mean, it is a story about how software engineers map out physical cities of silicon.
It is entirely geometry and physics bending to the will of code. And I want to give you, the listener, a little teaser for where this is all heading.
Oh, this is the best part.
Yeah, by the end of this deep dive, we are going to explain a really counterintuitive design trick called the elongation snake,
Right, the snake.
which involves deliberately adding like more wire to a chip, creating these little squiggly detours as the ultimate secret to making it run perfectly.
I know it sounds completely backward when you first hear it. You would think the goal is always the absolute shortest path.
Yeah, of course.
But once you understand the physics of electricity at that microscopic scale, it is a brilliantly elegant solution.
Okay, let's unpack this because before we can understand the algorithm, we need to understand the physical problem it's actually trying to solve on the silicon itself.
Exactly.
So the core concept here is clock tree synthesis, or CTS.
Right. So every synchronous digital circuit, which is basically every modern computer chip, relies on a clock. You can think of the clock source as the heartbeat of the chip.
Okay.
It's a central metronome casing everything.
And that heartbeat has to reach millions, sometimes billions of endpoints, right?
Right.
Which the blueprints refer to as sinks or flip-flops.
Yeah, the sinks are the individual physical components on the chip that actually do the processing or, hold the memory.
Right.
They all need to receive that heartbeat to know exactly when to move data to the next step.
So the analogy I was thinking of when reading through these sources is think of clock tree synthesis like the conductor of an enormous orchestra.
Oh, I like that.
Yeah, so the conductor is the clock source. And you have thousands of musicians, the sinks spread out all over a massive stage.
Check.
The conductor's job is to ensure every single musician plays their note at the exact same target millisecond, regardless of whether they are sitting right in the front row or way up in the very back balcony.
That is a perfect way to visualize it. And, if we carry that orchestra analogy a step further, think about what happens if the timing is off.
It's a mess.
Exactly.
Mhm.
If the violins play their note a fraction of a second before the cellos, you get a dissonant mess. In a computer chip, if one component receives the clock signal a fraction of a nanosecond before another
You get a data collision.
right, information is overwritten, the app crashes, your phone freezes.
Wow. So the stakes are incredibly high. The synchronization has to be completely flawless.
It does. And what's fascinating here is how the sources define the primary objective of this massive coordination effort. It's called prescribed skew.
Prescribed scheme.
Yeah. Now, skew is the difference in arrival time of the clock signal between any two syncs.
But wait, you want everyone to get the signal at the exact same time, right? Like zero skew.
Well, historically, yeah. Zero skew was the ultimate goal.
Yeah.
You wanted the heartbeat to arrive everywhere instantaneously. But modern chip design is far more nuanced.
Really?
Yeah, the blueprint explicitly points out that prescribed skew is not necessarily zero.
Huh.
Sometimes, to prevent different parts of the chip from glitching or interfering with each other or even just to manage heat, you actually want one section to receive the clock signal, a tiny, precisely calculated fraction of a nanosecond after another section.
Oh, wow.
So it's not just about everyone getting the signal instantly. I mean, it's about everyone getting it at a precisely calculated time relative to each other.
Okay, so the conductor isn't just waving the baton and saying play now. They're saying like violins play now and cellos play exactly
Yeah.
1 microsecond later.
Right, exactly. That level of intentional delay is crucial. And, alongside hitting those exact prescribed skew targets. The algorithm has two other massive constraints.
Okay.
It must ensure minimum wire length.
Right, to save space.
To save space, yeah, but also you want to use the least amount of copper or conductive material possible to keep power consumption low.
Got it.
And finally, it must create a balanced tree topology, ensuring the physical paths have equal structural delays.
Man, that is a colossal coordination problem. You have thousands of tiny endpoints scattered randomly across a 2D plane, right?
Hmm.
And you need to connect them all to a single central point with perfectly timed wire lengths while using the absolute minimum amount of wire. How does a computer program even begin to organize that mess?
Well, it starts by divide and conquer. The very first algorithmic step detailed in the blueprints is called algorithmic sorting via balance by partition.
Balance by partition.
Yeah, it basically needs to organize the chaos.
I was looking at the diagrams for this in the slides, actually. The algorithm takes all these physical endpoints, it structures them cleanly using object oriented programming, right? Like with sync and tree node classes, tracking positions, and capacitances.
Exactly. It builds a clean data structure first.
Right, and it tracks their positions on the board and starts sorting them. But the way it sorts them felt overly complicated to me. It doesn't just group things that are next to each other.
No, it approaches the board much more systematically.
Right, it splits the whole board of nodes down the middle on the x-axis, drawing a vertical line. Then for each of those halves, it splits them across the y-axis with a horizontal line.
Yep, alternating.
Then x again, then y again. It makes this really rigid grid pattern. So my question is, why can't we just group endpoints by whatever is closest in a circle?
On a cluster.
Yeah, like just draw a little boundary around a localized cluster of nodes and call them a group. Why this rigid alternating x, then y split?
It comes down to the sheer scale of the math involved.
Wait.
I mean, if you just draw circles to find clusters, the computer has to constantly recalculate the distances between every single node and every other node on the board to find the absolute closest pairs.
Oh, I see.
For 10 nodes, that's easy. For 10 million nodes, the number of distance calculations grows exponentially. A computer would take years to map a single chip.
Oh, because every time you group two nodes, you have to measure everything all over again for the rest of them.
Precisely. Sorting along alternating axes, slicing the board in half horizontally, then vertically, over and over, it guarantees a very specific, incredibly efficient mathematical property. It scales logarithmically.
Logarithmically, meaning that as you add more and more nodes, the time it takes the computer to sort them doesn't spiral completely out of control.
Right. The blueprints describe this as an O of n log n time complexity.
O of n log n.
Yeah, it is incredibly fast. By slicing x, then y, then x, the algorithm is mathematically guaranteed to build a perfectly balanced binary tree topology every single time.
Wow.
It pairs up the nodes evenly across the entire chip without wasting computing power, guessing which nodes are a millimeter closer to each other.
So it's not necessarily finding the absolute perfect localized circular cluster every single time, but it's finding a mathematically balanced grouping at a speed that makes designing a modern smartphone chip actually possible.
Yeah, it sets the stage beautifully. Now you have a logical pairing of all the endpoints. You know which nodes are going to be siblings sharing a parent wire.
Right.
But you haven't actually drawn any physical wires on the map yet. You just have the organizational chart.
And that brings us to the absolute core of the blueprints, the DME algorithm, deferred merge embedding.
Yes.
And here's where it gets really interesting, because the algorithm has to figure out where to place a wire intersection, the parent node, but it hasn't placed the wires connecting it to the grandparent yet.
It is a classic chicken and egg problem in physical design. I mean, how do you optimally place a point on a map when its ideal location depends on another point further up the chain that hasn't even been placed yet?
You can't.
Right. And if you guess wrong, the timing of the entire chip is ruined.
So the answer is right in the name, deferred. You procrastinate. You defer the decision. The DME algorithm solves this in two distinct phases, right? Phase one is the bottom-up merge.
Exactly. Walk us through how that works physically on the chip from the endpoints up to the center.
Okay, so the way I understood it from the diagrams, imagine you and a friend are trying to pick a restaurant to meet at for dinner.
Okay.
But you have a very strict constraint.
Mm-hmm.
You both must drive exactly 15 minutes to get there, so neither of you feels slighted.
Naturally.
Right. Now, instead of just guessing a specific address, looking at a map, and seeing if the math works out, you draw a 15-minute travel radius around your house.
Right.
Your friend draws a 15-minute radius around their house. Where those two shapes overlap, That's your merging segment.
I love that analogy. It perfectly captures the logic. In the DME algorithm, they use what's called Manhattan distance projections.
Manhattan distance.
Yeah, because wires on a chip can't run diagonally. They have to run in rigid vertical and horizontal lines, like a taxi navigating the grid of streets in Manhattan.
Okay, so the algorithm computes these overlapping merging segments for every single pair of nodes, starting from the outermost sinks at the bottom of the tree and working its way all the way up to the clock source in the center. Crucially, as the slides show, a merging segment isn't a single dot on the map. It's a dashed line bounding box representing all mathematically valid locations that would maintain that prescribed skew timing constraint.
You are capturing the exact set of possibilities. You aren't picking the final restaurant address yet. You are just defining the physical neighborhood where the restaurant must be located for the 15-minute travel time to work out perfectly for both of you.
Right, you defer the exact choice. You keep moving up the tree and making larger and larger bounding boxes of possibilities, merging the neighborhoods together. That's phase one.
And that is exactly what makes phase 2 possible, the top-down embed.
So once you finally reach the clock source at the very center of the chip, you start working your way back down the tree.
Because now you have the full context of the entire map. In phase 2, the algorithm starts at the root, the clock source.
Okay.
It looks at the very first merging segment, that bounding box of possibilities we drew, and it simply asks, what exact physical coordinate inside this neighborhood is absolutely closest to the clock source?
Oh, I see.
And it places the node right there. Then it looks at the children of that node, looks at their bounding boxes, and picks the coordinate closest to the parent.
So it's finally picking the restaurant addresses all the way down the chain. And because it's always picking the absolute closest valid point inside those overlapping radii.
It systematically minimizes the total wire length across the entire chip. It's a beautiful piece of logic.
Yep.
You defer the commitment until you have perfect information, and then you strike.
That's brilliant.
And from a software engineering perspective, the space complexity remains a sleek O of n.
Just O of n.
Yeah, because the amount of computer memory required to run this massive algorithm remains incredibly low. It doesn't need to memorize a billion different routing paths. It just stores a single clean map of these bounding boxes.
Which is critical because if this algorithm fails to minimize that wire length, the phone in your hand right now would be burning through its battery in minutes.
Oh, absolutely.
Those wires would be taking incredibly inefficient routes, generating excess heat and draining power.
The physical consequences of bad routing are immediate and severe.
So we have this elegant algorithm mapping out where the wires should go using these bounding boxes. But finding the physical paths on a 2D map is only half the battle.
Right.
Electricity is fast, but it doesn't travel instantly. It takes time to move through a wire. How does the algorithm actually calculate the speed of the electrical signals to ensure those 15-minute travel radii are accurate?
That is where we transition from pure abstract geometry into heavy physics. The sources outline a software architecture concept called the strategy pattern.
Yeah, I was looking at the physics models in the blueprints, and the core algorithm doesn't actually seem to know how to calculate delay at all.
Well, if we connect this to the bigger picture of software design, you want to keep your complex routing math completely separate from your physical physics models.
Makes sense.
The core DME algorithm relies on pluggable delay calculators to do the heavy lifting. The blueprints provide two different models for this, a very simple linear model and a vastly more complicated Elmore model.
The linear model seems incredibly straightforward. The formula is basically just delay equals k times L. It's an O of 1 calculation.
Very simple.
It essentially assumes that if a wire is twice as long, it takes exactly twice as much time for the signal to cross it, a simple 1-to-1 ratio. But then you look at the Elmore model, and the math looks incredibly intimidating.
Oh.
It has this whole formula with R times C times L squared over 2 plus R times L times C load. Why does the math suddenly get so much heavier?
Let's break down why that matters physically. The linear model is basically a fantasy. It assumes wires are perfect conductors.
Right.
But wires on a real microchip aren't perfect. They have resistance, meaning the material itself physically pushes back against the electrical current, and they have capacitance, meaning the wire and the surrounding silicon sort of act like a sponge, absorbing and holding a little bit of the electrical charge as it passes through.
So it's like trying to push water through a spongy hose instead of a solid PVC pipe. Some of the water pressure gets lost, expanding the hose itself.
That is a brilliant visual. Now imagine what happens when you double the length of that spongy hose.
Yeah.
You don't just double the physical distance the water has to travel.
Right.
You also double the resistance of that hose, NED. You double the amount of sponge material soaking up the water.
Oh, so the delay compounds on itself.
Exactly. The delay doesn't just double, it quadruples.
Right.
The physics formula shows that delay scales quadratically with length, that L squared term.
L squared, right.
A long wire isn't just a little slower, it is exponentially punishing to your timing. The Elmore delay model mathematically calculates this real-world resistance capacitance network. It accurately predicts how the spongy hose will behave.
Which makes total sense. You need that realistic physics bound to build an actual piece of silicon. But that brings up a question for me.
Sure.
If the Elmer model is the only one that reflects reality, why do the blueprints even bother building the simple linear model? Isn't it just a less accurate, simplified toy?
It might seem that way, but the linear model is absolutely crucial for the development process. Because the linear math is so simple, it allows engineers to run lightning-fast, quick estimations during the early testing phases.
Oh, I see.
You can simulate the entire chip's topology in seconds just to see if your basic grouping logic is working.
Ah, so you use the cheap linear model to make sure the general structure of the tree is balanced, and then you plug in the heavy Elmore model when you need to generate the exact physical blueprints for the factory.
Exactly. You swap the calculator plug-in, and the core logic remains completely untouched. By utilizing this strategy pattern to decouple the geometry from the physics, the architecture achieves what the blueprints call mathematical purity and infinite extensibility.
Mathematical purity.
Yeah, meaning in 5 years, if someone invents a completely new physical material for microchips with totally different delay physics.
You don't have to rewrite the entire DME routing algorithm. You just write a new delay plugin for that specific material.
Right. The architecture is totally future-proofed.
Okay, so we have our optimal map, we have our highly accurate Elmore physics calculator tracking the spongy hose effect. But what happens when the real world refuses to cooperate with the math?
It happens a lot.
Because the blueprints have an entire section dedicated to boundary conditions. And this is where we finally get to the elongation snake.
Ah, yes. This is where the algorithm has to bend physical reality to maintain its strict mathematical rules.
So we're back in phase one, building those merging segments, the restaurant travel radii. The algorithm is calculating the exact tapping point where two child wires should merge into a parent wire.
Right.
But sometimes, due to the different capacitances of the endpoints or the weird distances involved, the math spits out a merge point that falls completely outside that neighborhood of possibilities we defined.
Exactly. The tapping point calculation yields a result where, like, extend left is less than 0 or greater than the distance. The ideal merging point is literally off the edge of the allowable map.
Right.
The algorithm throws a warning flag and realizes one signal is traveling way too fast compared to the other.
It calculates that one branch's delay is vastly different. And it flags this with node.need underscore elongation equals true.
Yes.
And to fix this massive imbalance, it literally draws a squiggly line and elongation snake to artificially increase the length of the shorter delay wire.
It intentionally forces the faster signal to take the scenic route.
So, what does this all mean? I have to admit, I'm a little confused here.
Okay, how so?
We just spent the entire second phase of the algorithm, the top-down embed, strictly dedicated to minimizing wire length to save power and prevent the phone from overheating.
True.
We just talked about how long wires are exponentially punishing because of the spongy hose effect. Now you're telling me that when the math gets tough, we deliberately add extra unnecessary snake-like squiggly wires to the chip. Isn't that completely ruining the optimization we just worked so hard for?
It is a fascinating contradiction, I'll give you that. But you have to remember the strict hierarchy of needs in clock tree synthesis. Minimum wire length is an incredibly important secondary optimization. Yes, timing is the supreme law. Prescribed skew is completely non-negotiable.
Because if the timing is off, the orchestra is dissonant, the data collides, and the chip crashes.
That's why the elongation snake acts as a highly calibrated speed bump. Imagine you have two electrical signals racing to a merge point. Signal A is arriving a fraction of a nanosecond too early compared to signal B because its physical path was just naturally easier.
It had less resistance.
Exactly. If you just let them merge naturally, your skew is ruined, the timing is broken.
So you make signal A run a little microscopic obstacle course?
You add the snake. That extra squiggly wire mathematically increases the resistance and capacitance of that specific branch. It intentionally creates a little more of that spongy hose effect, perfectly slowing down the signal, so it arrives at the exact same target picosecond as signal B.
And the genius part of this, looking at the diagrams, is that it does this without shifting the original bounding box.
Yes, that is key.
It solves the localized timing problem right there in the squiggles without forcing the parent node to move. Because if the parent node had to move to compensate, it would cascade and ruin the timing for the entire rest of the carefully mapped tree.
It isolates the fix. It bends the physical wire to preserve the purity of the entire mathematical topology above it. It's a brilliant compromise between abstract geometry and the harsh physical reality of electricity.
It really is. Taking a massive, chaotic plane of millions of sinks, organizing them with perfect logarithmic efficiency, drawing out millions of possible overlapping routes without committing too early,
Yep.
applying real world quadratic Elmore physics model to calculate the speed of light through silicon, and then, when necessary, deploying invisible elongation snakes to ensure every single signal arrives on time.
And this entire invisible geometric choreography is happening billions of times a second. Every time you scroll smoothly on your phone, every hour of battery life you squeeze out of your laptop, it is built on the back of this precise microscopic routing. If the algorithms in these blueprints fail, your devices simply do not function. It is the silent, unseen infrastructure of the modern world.
It's incredible to think about the sheer volume of architectural engineering just sitting casually in your pocket right now.
It is mind boggling.
Right.
But this raises an important question, especially when you look at the future enhancement section at the very end of the blueprints.
Oh, yeah. What's the next frontier for this kind of algorithmic routing?
Well, the algorithm we just explored is phenomenally complex, but it's fundamentally solving a two-dimensional problem for a single clock heartbeat.
Right.
The blueprints point toward the bleeding edge of silicon design, variation-aware components, and multi-clock domains where different parts of the chip are running at entirely different frequencies.
Like having five different conductors trying to lead different sections of the orchestra at different tempos simultaneously, but they all still have to harmonize perfectly at key moments.
Exactly that. And even more challenging, the physical design world is hitting the limits of how small we can shrink transistors. So they're moving away from flat planes and starting to stack these chips in 3D to save space.
Oh, wow. So the Manhattan taxi grid isn't just X and Y anymore, it's Z. You have to route these incredibly sensitive clock signals vertically through microscopic layers of silicon.
Yeah. How much further can mathematical purity stretch before the physical limitations of heat generation, electrical interference, and three-dimensional space break the blueprint entirely?
That is a staggering thought. The orchestra is no longer on a single flat stage. They are suspended in a multi story skyscraper, and they still all have to hit the exact same note at the exact same millisecond without the building catching fire.
It will require entirely new algorithmic paradigms and even more complex physical models. The elongation snake might just be the beginning.
Well, that is certainly something to mull over the next time you tap an app on your screen and expect it to open instantly. Just remember that behind that simple, everyday action is a conductor desperately trying to keep millions of invisible signals in perfect time, occasionally forcing them to slither through an elongation snake just to keep the whole performance from falling apart. Thanks for joining us on this deep dive.